a quiet archive record. Tonight, we pass into a world that asks nothing of you. No urgency, no weight, just the quiet unfolding of a story. Far beyond the bright planets, the solar system does not end in a clean line. It thins, spreads, and becomes a wide, cold geography of ice and rock. This region is called the Kuiper Belt. It is not a single ring, but a broad zone shaped by gravity, collisions, and long spans of time. Here, small worlds move in slow arcs, and sunlight arrives as a faint, pale pressure. Some of these objects are leftovers from the first days of the solar system. Some have been scattered into strange paths by Neptune. Some are locked into steady rhythms that keep them stable for billions of years. In this episode, we take a clear, grounded tour of what the Kuiper Belt is, how it formed, how it stays organized, and why it matters. We focus on 10 striking realities that reveal the belt as a living boundary between planets and deep space. Tonight, we go through 10 mind-blowing facts about the Kuiper Belt. To understand the Kuiper Belt, it helps to start with a simple picture of scale. If you could stand at Earth and look outward, the familiar part of the solar system would appear crowded and bright. The inner planets orbit close to the Sun. The asteroid belt sits between Mars and Jupiter. Jupiter, Saturn, Uranus, and Neptune circle farther out, each one taking longer to complete a year. Past Neptune, the paths of the planets give way to something quieter. The Kuiper Belt begins near Neptune's orbit and stretches outward for a long distance, roughly from about 30 astronomical units to about 50 astronomical units from the Sun, depending on how you define its edges. 1 astronomical unit is the average distance from Earth to the Sun. So we are talking about a region that starts at about 30 times Earth's distance from the Sun and extends to around 50 times that distance. Even that description can make the belt sound like a thin ring, as if it were the edge of the system. But the belt is thick. It has depth above and below the plane where the planets orbit. Its objects have orbits tilted at different angles, and their distances from the Sun change as they travel. If you could draw it in 3 dimensions, it would look like a wide, puffed-up disk, not a razor-thin hoop. The first mind-blowing fact is that the Kuiper Belt is not empty space with a few scraps floating around. It is a structured population of millions of bodies, many of them too small to see directly with today's telescopes, but present in large numbers. When people first hear about the belt, they sometimes imagine a tight swarm, like the asteroid belt in science fiction movies, with rocks packed close together. The reality is the opposite. The Kuiper Belt is vast. The objects are spread out so widely that if you were traveling through it in a spacecraft, you would spend most of your time in open space. But the number of objects is still enormous. There are likely tens of thousands of bodies, larger than 100 kilometers across, and many more smaller ones. The belt is a record of what the early solar system left behind. This leads to the second mind-blowing fact. The Kuiper Belt is one of the best places to look for ancient material that has changed very little since the solar system was forming. In the inner solar system, the Sun's heat, the impacts of large bodies, and the repeated melting and reshaping of planets have erased many early clues. But in the Kuiper Belt, temperatures are extremely low. Many objects are too small to have been heated much from the inside. Their surfaces can preserve ices and chemistry that formed in the early nebula. That does not mean they are untouched. Some have been hit broken and reassembled. Some have been altered by radiation and by the slow cooking of sunlight. But the belt still contains old building blocks. It is a deep freezer of early history. To see why this matters, imagine trying to understand how a city was built. If every early street had been replaced and every old brick had been melted down, you would be forced to guess. But if you found an untouched warehouse filled with original materials, blueprints, and tools, you could reconstruct the story. The Kuiper Belt is that kind of warehouse for the solar system. The third mind-blowing fact is that the Kuiper Belt does not merely sit beyond Neptune. It is shaped by Neptune in a very specific and measurable way. Neptune is the outermost giant planet, and its gravity acts like a slow-moving sculptor. In the early solar system, Neptune likely migrated outward. That migration did not happen in a straight line, and it did not happen instantly. As Neptune moved, it pushed and pulled on the smaller bodies beyond it. This process captured some objects into orbital resonances. A resonance is a repeated rhythm between two orbits. For example, Pluto is in a 2 to 3 resonance with Neptune. That means for every 2 orbits Pluto makes around the Sun, Neptune makes 3. The timing keeps Pluto from ever getting too close to Neptune, even though their paths cross in a simple drawing. Resonances are not rare accidents. They form patterns in the belt. Entire groups of objects share the same resonance, locked into stable rhythms. This is mind-blowing because it means the belt is not just a pile of leftovers. It is organized like a library shelf where certain kinds of books end up in specific sections. The presence of these resonant groups is strong evidence that Neptune moved in the past. Without migration, many of these captured patterns would be difficult to explain. The fourth mind-blowing fact is that Pluto is not the king of the Kuiper Belt, but it is also not an oddball exception. Pluto is one member of a broad family now called dwarf planets, and its existence pointed to a much larger population. When Pluto was discovered in 1930, it was first thought to be a planet, and for decades it stood alone. But as telescope surveys improved, more distant objects were found. In the 1990s and 2000s, discoveries accelerated. Astronomers found bodies like Quaoar, Sedna, and Eris. Some of these are comparable to Pluto in size. Eris is slightly smaller in radius but similar in mass. The discovery of Eris played a major role in the 2006 decision to define the term planet more strictly. The key point here is that Pluto is part of a population. It is one of the largest known Kuiper Belt objects, but it sits among many other worlds. The belt is not a small, minor feature. It contains planetary-sized bodies, small moons, and complex systems. This brings us to the fifth mind-blowing fact. Many Kuiper Belt objects are not solitary. A large fraction of them are in binary pairs, and some are in systems with multiple bodies. Two objects can orbit a shared center of mass, drifting around each other while together they orbit the Sun. Some binaries are tight, with the bodies close together. Others are wide, with the partners separated by tens of thousands of kilometers. The Kuiper Belt is one of the best places to find wide binaries, because the environment is less disturbed than the inner solar system. The existence of these pairs tells us about the early conditions. Wide binaries are fragile. They are easily broken apart by close gravitational encounters. If many survive, it suggests that the belt was not violently stirred up everywhere for the entire age of the solar system. It suggests regions of long-term calm. Binary systems are also valuable because they let us measure mass. If you can watch two bodies orbit each other, the details of their motion reveal their combined mass. When you combine mass with size estimates, you can infer density. Density tells you how much ice, rock, and empty space the body contains. Some Kuiper Belt objects appear to be porous, like loose piles. Others are denser and more compact. The belt contains a range of internal structures. The sixth mind-blowing fact is that the Kuiper Belt is not the only distant reservoir of small bodies. It may be the inner edge of a larger story. Beyond the belt, there is the scattered disk, a population of objects with more stretched, eccentric orbits. Some come close enough to Neptune to be tugged around, while their farthest points take them much farther out. And beyond that, in theory, there is the Oort cloud, a far more distant spherical shell of icy bodies that may extend halfway to the nearest stars. The Kuiper Belt is closer, flatter, and more directly tied to the plane of the planets. But it connects to these other populations through the slow reshaping of orbits. The scattered disk is especially important because it provides many of the objects that become short-period comets. When a body's orbit is nudged inward, it can be sent into the inner solar system, where sunlight heats its ices, releasing gas and dust. The bright coma and tail of a comet are temporary. The body itself is a small, dark nucleus, but it carries material from the cold outskirts. In this way, the Kuiper Belt and related regions supply visiting messengers that cross the sky. The seventh mind-blowing fact is that the Kuiper Belt has a sharp outer edge, sometimes called the Kuiper Cliff. Surveys show that the number of objects drops off beyond about 50 astronomical units, much more sharply than a simple, gradual thinning would suggest. This cliff is surprising because there is no obvious physical wall at that distance. Space does not suddenly change. So why does the population thin so quickly? Several ideas have been proposed. One is that Neptune's migration cleared and shaped the region, leaving an edge where stable orbits become rare. Another is that the solar system formed in a cluster of stars, and a nearby star passed close enough early on to truncate the disk of material. Another possibility is that the original disk of building blocks simply did not extend much beyond that region, or that the density was too low to build larger bodies. The outer edge is a clue. It is like finding a cut in a piece of fabric and trying to infer what made it. The eighth mind-blowing fact is that the Kuiper Belt contains objects with wildly different surface colors. Some are very dark and neutral, like charcoal. Others are reddish, as if coated in rust-colored material. This redness is thought to come from complex organic compounds produced when radiation breaks apart simple ices and rearranges the fragments. Over time, cosmic rays and ultraviolet light can turn icy mixtures into tar-like residues. The result is a surface that can become red, brown, or black. Color differences suggest different histories. Some objects may have formed closer to the sun and been scattered outward, carrying different compositions. Others may have formed farther out, retaining more volatile ices. Some may have been resurfaced by impacts, exposing fresher ice beneath. The belt is not uniform. It is a mix of families and origins, and color is one of the strongest visible signs. The ninth mind-blowing fact is that the Kuiper Belt is not mainly a place where planets formed, but a place where planetary formation stopped. In the region of the inner solar system, small bodies collided, grew, and built the terrestrial planets. Farther out, Jupiter and Saturn gathered huge amounts of gas and became giants. But beyond Neptune, the process did not complete. The material was too spread out. Collisions happened too slowly. Neptune's gravity stirred the orbits and increased relative speeds, which can make collisions destructive rather than constructive. In other words, the Kuiper Belt is a fossil of an unfinished world-building process. It shows us what happens when you have a disk of material, but not enough time or density to form a true planet. The belt's objects are the remnants that never merged into a larger body. The 10th mind-blowing fact is that the Kuiper Belt is influencing the present-day solar system in subtle ways. It is a source region for comets. It is a gravitational environment that still holds objects in resonances and stable configurations. And it is a testbed for theories of how planetary systems evolve. When astronomers study other stars, they often detect debris disks, belts of dust, and small bodies that glow in infrared light. These disks are thought to be shaped by unseen planets. Our Kuiper Belt is a nearby example of the same kind of structure, but seen from within. By understanding it, we learn how typical our system might be. Now, with those 10 realities in mind, we can move through the Kuiper Belt in a more detailed way, as if we are tracing a route across a cold map. The Kuiper Belt begins close to Neptune's orbit, but not directly at it. Neptune orbits the Sun at about 30 astronomical units. Just beyond Neptune, there is a region that is relatively depleted, often called the Kuiper Gap. It is not completely empty, but it has fewer stable objects because Neptune's gravity strongly influences orbits in that zone. Farther out, the classical belt begins. These are objects with relatively stable, less stretched orbits, not strongly scattered by Neptune, and not necessarily in strong resonances. They are sometimes divided into a cold classical population and a hot classical population, not by temperature, but by orbital inclination. The cold classical objects have orbits that are not tilted much. The hot classical objects have orbits tilted at larger angles. This difference is important because it hints at different formation paths. The cold classical population may have formed largely in place, remaining in a calm region where inclinations stayed low. The hot classical population may include bodies that formed closer to the Sun and were later scattered outward, their orbits tilted and excited by interactions with the giant planets. This is an example of how motion becomes a clue. You cannot easily look at these objects up close, but you can measure their orbits precisely, and the orbit becomes a fingerprint. When you picture the belt, it helps to think in terms of speed as well as distance. At Earth, an orbital speed around the Sun is about 30 kilometers per second. In the Kuiper Belt, orbital speeds are much lower, on the order of a few kilometers per second. A year out there can last hundreds of Earth years. Neptune takes about 165 Earth years to orbit once. Pluto takes about 248. Objects farther out take even longer. This slow motion means that changes happen on long time scales. Gravitational nudges can take millions of years to show their effects. Collisions are rare, but the slow pace also means that stable patterns can survive for a very long time. Resonances create some of the most striking patterns. The 2 to 3 resonance is one of the most famous because of Pluto. Objects in this resonance are called plutinos. There are also objects in other resonances, like 1 to 2, 2 to 5, and 3 to 5. These resonant groups help explain how objects avoid close encounters with Neptune. The resonance acts like a timing lock. Even if the orbit crosses Neptune's distance at some point, the object is never at that crossing point when Neptune is there. This is a deep point. The solar system is not a set of isolated circles. It is a web of timing relationships. In the Kuiper Belt, where objects are small and easily perturbed, these timing relationships can determine whether an orbit survives or is eventually ejected or scattered. The story of Neptune's migration is one of the key reasons the belt is so scientifically valuable. In many models, the giant planets did not form exactly where we see them now. They formed in a disk of gas and small bodies. As they interacted with that disk, exchanging energy and momentum, their orbits shifted. Jupiter may have moved inward and then outward in a pattern sometimes called the grand tack. Neptune and Uranus may have moved outward. During these shifts, resonances swept through space, capturing objects or pushing them away. The Kuiper Belt today contains the evidence of that sweeping. You can think of it like a moving snowplow. If you push a plow across a field of loose snow, you do not just move the plow, you also create ridges, piles, and cleared strips. Neptune was like a plow, moving through a field of small bodies. The ridges and piles are resonant populations and scattered objects. The cleared strips are depleted zones. One reason Pluto's orbit is so fascinating is that it is tilted and stretched. Pluto's orbit has a significant inclination, and its distance from the Sun changes a lot over its orbit. At its closest, it can be closer than Neptune. At its farthest, it goes much farther out. Yet it remains stable because of resonance. This means that even orbits that look chaotic can be orderly when you consider timing. Pluto also has a complex system of moons. Its largest moon, Charon, is so big relative to Pluto that the two are often described as a double dwarf planet. They orbit a point in space that lies between them, outside Pluto itself. This kind of system is rare among planets, but more common among smaller bodies. The formation of Pluto and Charon is thought to involve a giant impact early in their history, similar in some ways to the impact that formed Earth's moon. If such an event occurred in the Kuiper Belt, it suggests that the early belt may have been more crowded, with collisions between large bodies. Beyond Pluto, there are other large objects with their own features. Eris has a moon named Dysnomia. Haumea is an elongated, rapidly spinning body with a ring and at least 2 moons. Haumea's fast spin and shape suggest it was involved in a major collision that stripped material away. Makemake is another large body with a reddish surface. Quaoar has a moon and may have a ring. These objects reveal that the Kuiper Belt is not a uniform collection of small rocks. It contains worlds with geology, rings, and moons. The presence of rings around small bodies is especially striking. Rings are often associated with giant planets like Saturn, but rings can form around smaller bodies as well, perhaps from debris created by impacts or from material that cannot gather into a moon because of tidal forces. Finding rings around Kuiper Belt objects expands our understanding of what kinds of systems can exist. Another key feature is the role of ices. In the Kuiper Belt, water ice is common, but there can also be carbon dioxide, methane, nitrogen, and other frozen volatiles. On Pluto, nitrogen ice forms glaciers and plains. Methane and carbon monoxide also exist. These ices can move and change with seasonal cycles, even at Pluto's distance. because sunlight still warms the surface slightly over long periods. Pluto's thin atmosphere can freeze out and return as it moves closer and farther from the Sun. Not every Kuiper Belt object is large enough to hold an atmosphere. Many are too small, but even small ones can have surfaces altered by sublimation, where ice turns directly into gas in vacuum when warmed. Over long times, this can drive changes. It can also create jets or release dust if conditions are right. The belt is not entirely static. The New Horizons mission provided the first close-up views of a Kuiper Belt object. New Horizons flew past Pluto in 2015. The images showed a world with mountains of water ice, smooth plains, and signs of active geology. Later, in 2019, New Horizons flew past a smaller Kuiper Belt object, originally called 2014 MU69 and later named Arakoth. Arakoth is a contact binary, two lobes gently stuck together, like two smooth stones pressed into one. Its shape suggests a gentle collision at low speed in a calm environment. The surface of Arakoth is reddish, likely coated in complex organics. This single object provided a direct snapshot of how some small bodies may have formed by slow accumulation rather than violent impacts. Arakoth also supports the idea that the cold classical belt may have been relatively undisturbed. A fragile contact binary with a smooth shape could have been disrupted by strong gravitational stirring. Its survival suggests that at least some part of the belt has remained calm since early times. This is a powerful clue. The outer edge of the belt, the Kuiper Cliff, remains one of the biggest puzzles. The drop in objects beyond 50 astronomical units suggests that either formation conditions changed or later processes removed bodies. Some models propose that the Sun formed in a cluster and that passing stars could have stripped away the outer disk. Another idea involves the influence of the galactic tide, the weak gravitational pull of the Milky Way's mass distribution, which can slowly alter orbits of very distant objects. But the Kuiper Cliff is closer than the region most affected by galactic tides. That is why the cliff is so intriguing. There is also the question of how the scattered disk and the belt relate. Some objects have orbits that take them far beyond the classical belt, but still bring them near Neptune at their closest approach. These objects can be repeatedly nudged by Neptune, which can increase or decrease their orbital energy. Over long times, some may be sent inward, becoming comets. Others may be sent outward, joining a more distant population. Then there are objects like Sedna, which have extremely distant and elongated orbits, with closest approach far beyond Neptune's strong influence. Sedna's orbit suggests some kind of early event, perhaps a passing star, or interactions in the Sun's birth cluster, or an unseen, massive body. Sedna is often discussed in the context of the hypothetical Planet 9. Planet 9 is a proposed planet-sized body far beyond Neptune, inferred from patterns in the orbits of some distant objects. The evidence is debated, and the planet has not been found. But the idea shows how the outer solar system remains partly unknown. The Kuiper Belt is not only a region to catalogue, it is a region that still raises questions. When astronomers search for Kuiper Belt objects, they face a simple challenge. These objects are small, dark, and far away. They reflect very little sunlight. Their motion across the sky is slow. To find them, astronomers take repeated images of the same patch of sky and look for points of light that move slightly relative to background stars. This is a patient method, and it has improved with better cameras and automated search algorithms. The discovered population is still incomplete. Surveys tend to find the largest and brightest objects first. Smaller objects remain hidden. This means that the true total mass of the belt is uncertain. But estimates suggest that the belt contains much less mass than would be needed to form a planet. This is one reason it is seen as an unfinished region. It likely began with much more material, but much of it was removed or scattered. One way material can be removed is through collisions that grind objects down into dust. Dust can then be pushed by sunlight and by interactions with the solar wind. Another way is through gravitational scattering by Neptune and other planets. Over time, small bodies can be sent inward or outward. The belt today may be a remnant of a larger original disk. The belt also serves as a comparison point for debris disks around other stars. Many stars have belts of dust and small bodies. Some show gaps and rings that suggest the presence of planets. When we see a bright ring in infrared around a young star, we are likely seeing collisions among small icy bodies, similar in concept to the Kuiper Belt. By studying our own belt, we can better interpret those distant observations. It is also worth noticing how the Kuiper Belt changes our intuitive sense of what a solar system is. For a long time, the solar system was presented as a neat set of planets, with the asteroid belt as a minor feature. The Kuiper Belt reveals that planetary systems can have broad, complex outskirts. The boundary is not simply the last planet. It is a region of small worlds that still reflect the system's past. If you could travel outward from the Sun, past the planets, and into the Kuiper Belt, you would see sunlight dim drastically. At Neptune, sunlight is about 1/900th as bright as at Earth. Farther out, it grows even weaker. The sun would still be a bright object in the sky, but it would not warm you. The background stars would be sharp points. The sky would be dark. And yet, even in that darkness, the belt is full of motion. Each object follows a path defined by gravity. Over millions of years, those paths can shift. Resonances can capture and release objects. Collisions can reshape bodies. Ices can shift and sublimate. The belt is not a dead zone. It is a slow system. Now, to keep the documentary arc grounded, we can focus on a few key questions. What is the belt made of? How is it organized? How did it become that way? And how do we study it? Composition is one of the most direct questions. Most Kuiper Belt objects are mixtures of rock and ice. Water ice is common, but because temperatures are low, other ices can survive as solids. Methane, nitrogen, and carbon monoxide are particularly volatile, meaning they can evaporate at relatively low temperatures. Larger bodies can hold on to these ices more easily because of stronger gravity. Smaller bodies may lose them over time. This creates a size-dependent pattern. Large dwarf planets can have volatile, rich surfaces. Smaller objects may be more depleted. Radiation from the sun and from cosmic rays can slowly process the surface. Over time, it can darken and redden it, building complex organics. Impacts can expose fresher material. In some cases, cryovolcanism may occur on larger bodies, where cold, icy materials flow like lava. Pluto shows hints of such processes. This means that even far from the sun, geology can happen. Organization in the belt is described by orbital elements. Astronomers measure semi-major axis, eccentricity, inclination, and other parameters. Semi-major axis is the average distance from the Sun. Eccentricity describes how stretched an orbit is. Inclination describes how tilted it is relative to the plane of the planets. When you plot these values for many objects, patterns appear. Resonant groups form clusters. Classical populations occupy certain bands. Scattered objects extend farther out with higher eccentricities. These patterns serve as constraints on models. If a model of Neptune's migration produces the wrong distribution of resonant objects, it can be rejected or adjusted. In this way, the Kuiper Belt becomes a test for the solar system's early dynamics. Another key clue is the presence of collisional families. In the asteroid belt, there are families of asteroids that share similar orbits and are thought to be fragments of a larger parent body that was broken apart. In the Kuiper Belt, collisions are rarer, but families exist. Haumea's family is a famous example. Several objects share similar orbital elements and surface properties, suggesting they came from a common collision. This tells us that even in the outer solar system, large impacts have occurred. As we move outward toward the edge of the belt, we also see the influence of resonances. The 1 to 2 resonance, sometimes called the Tutino resonance, lies near 48 astronomical units. Objects in this resonance complete one orbit for every 2 orbits of Neptune. This resonance region is one of the features near the belt's outer area. The distribution of objects near resonances helps explain stability and capture. Beyond the classical belt, the scattered disk extends farther. Objects here often have perihelia, their closest approach distances near Neptune's orbit, but their aphelia, farthest distances, can be much farther out. The scattered disk is dynamic. Neptune can still influence these objects. Over time, some may be sent even farther out into detached orbits that no longer come near Neptune. Detached objects are a special group. Their perihelia are far enough from Neptune that Neptune cannot easily scatter them now, yet their orbits are still elongated. This suggests past events. A passing star, an early phase of a more massive disk, or interactions with migrating planets could have lifted their perihelia. These objects are rare and hard to find, but they hold some of the strongest clues about the solar system's earliest environment. When you hear the phrase mind-blowing facts, it can sound like a list, but in a continuous documentary flow, the facts become a set of revelations that deepen the picture. One revelation is that the belt is organized. Another is that it preserves early material. Another is that it contains worlds with geology. Another is that it holds fragile binaries that tell us about calm regions. Another is that its outer edge is sharply cut. Each one adds a piece. If we step back and ask why the belt exists at all, the answer is tied to how the solar system formed. The sun formed from a collapsing cloud of gas and dust. A disk formed around the young sun. In that disk, dust grains collided and stuck, forming larger aggregates. Over time, these grew into kilometer-sized planetesimals. In the inner disk, growth was fast. In the outer disk, growth was slower, because orbital periods were longer and material was more spread out. The giant planets formed by gathering solid cores and then capturing gas. As they formed, they affected the disk. Their gravity stirred up planetesimals. Some were thrown inward, some outward. The belt region is where many planetesimals ended up, but with reduced density compared to the early disk. Neptune's growth and migration likely stirred the region strongly, preventing full planet formation beyond it. Another important process is resonance sweeping. As Neptune moved outward, its resonances moved with it, sweeping through regions of the disk. Objects could be captured in resonances and transported outward or pushed into new orbits. This can explain why some objects in the belt may have formed closer in. It can also explain why the cold classical population might be distinct, if it formed in place and was not swept up. One of the strongest pieces of evidence for a distinct cold classical population is their physical properties. Some cold classical objects have very red surfaces and a higher fraction of binaries. They also tend to have lower inclinations. This combination suggests they formed in a specific region and remained there. In contrast, the hot classical population has a wider range of inclinations and colors. This suggests mixing, as if bodies from different formation zones were scattered into that region. The belt, then, is not one clean population. It is layered like sediments deposited in different eras. The study of the Kuiper Belt is also limited by distance. We often rely on indirect measurements. Size estimates come from brightness and assumptions about reflectivity, called albedo. A bright object could be large and dark or smaller and reflective. Thermal measurements in infrared can help break this ambiguity because they measure how much heat the object emits. Combined with brightness, this can yield better size estimates. Occultations are another method. If a Kuiper Belt object passes in front of a distant star, it can block the star's light briefly. By measuring the timing and shape of the dip in brightness, astronomers can infer the object's size and shape, and sometimes detect atmospheres or rings. Occultations require precise predictions of orbits and careful observation, but they can reveal surprising details. This is how rings have been detected around some distant bodies. A star's light can dip multiple times as ring material passes in front. Even a thin ring can produce a measurable signal. In this way, the Kuiper Belt becomes not just a theoretical region, but a place with observable structures. As we move through the belt in imagination, we can also consider how it would look from close range. Many Kuiper Belt objects are dark. They reflect little light. Their surfaces can be coated in processed organics. Some may have patches of bright ice. Impacts can reveal fresh material. The temperature is low enough that nitrogen and methane can freeze, but sunlight still reaches them, so over long spans, some ices can move. The environment also includes micrometeoroid impacts and radiation. Over billions of years, this can change the surface texture, darken it, and alter chemistry. Space weathering is a slow process, but it matters. Now consider comets. Many short-period comets, those with orbital periods of less than about 200 years, are thought to come from the Kuiper Belt and scattered disk. When such a body is nudged inward, it can become active. The ices near its surface sublimate, carrying dust out. The object's brightness can increase dramatically, making it visible from Earth. But each passage near the Sun can also remove material, slowly eroding the comet. Eventually, a comet can become inactive, leaving behind a dark, asteroid-like body. In this way, Kuiper Belt objects can become visitors to the inner solar system, and sometimes even impact Earth. This connects the belt to the history of impacts and the delivery of water and organics. The Kuiper Belt is far away, but it has consequences. The belt also matters for spacecraft navigation and exploration. New Horizons demonstrated that reaching the belt is possible, but it requires careful planning. The travel time is long. The spacecraft must be fast. It must conserve fuel for trajectory adjustments. It must operate far from the sun, where solar panels are less effective, requiring nuclear power sources. Future missions could explore more Kuiper Belt objects, perhaps orbiting one or returning samples. Sample return would be extremely challenging due to distance and time, but even a flyby can reveal a great deal. The most powerful data comes from close-range images, spectroscopy, and mass measurements. As our view improves, we may find more dwarf planets and more strange systems. There may be bodies with rings, bodies with unusual spins, bodies with high densities, and bodies with unexpected chemistry. Each discovery can force us to adjust our models. The belt also helps answer a basic question. Is our solar system typical? When we look at exoplanet systems, we see a wide variety. Some have hot Jupiters close to their stars. Some have super-Earths packed close in. Some have debris disks. The Kuiper Belt shows that our system has a significant outer debris region. Whether that is common is still an open question. But the processes that shape it, migration and resonance, appear to be common in planetary dynamics. One of the simplest mind-blowing aspects is the idea that beyond the planets, there are still worlds, some large enough to be nearly planetary in size, moving in darkness. The solar system is larger and more populated than the classic planet list suggests. We can also address a common misunderstanding. The Kuiper Belt is sometimes confused with the asteroid belt. The asteroid belt sits between Mars and Jupiter. It is mostly rock and metal, though some asteroids contain water and other volatiles. The Kuiper Belt sits much farther out and is dominated by ices mixed with rock. The two belts formed under different conditions and have different histories, but both represent regions where planet formation did not proceed to completion, in part because of the influence of nearby giant planets. Another misunderstanding is the idea that the belt is the source of all comets. In reality, long-period comets, those that take thousands or millions of years to return, are thought to come from the Oort cloud, far beyond the Kuiper Belt. Short-period comets, especially Jupiter family comets, are tied to the Kuiper Belt and scattered disk. This distinction matters because it shows that the solar system has multiple reservoirs of icy bodies at different distances. When you consider the belt's mass, it is surprisingly low. Estimates suggest that the current belt has only a small fraction of Earth's mass, perhaps a tenth or less. Yet the belt must have started with much more material to form the objects we see. This implies that most of the original mass was removed, likely by scattering and by collisions. This is a reminder that the solar system's present structure is the outcome of loss as well as growth. Loss is sometimes as important as formation. The planets we see today are survivors of a chaotic early period. The Kuiper Belt is both a survivor and a remnant, a zone that kept enough objects to preserve history, but lost enough mass to prevent planet formation. The belt's sharp outer edge might be one sign of such loss. If a passing star stripped the outer disk, that would remove mass beyond a certain point. If Neptune's migration and resonances cleared objects, that would also sculpt the distribution. One way to test these ideas is to look at the inclinations and eccentricities of objects near the edge. If a star passage occurred, it might leave a characteristic pattern. If Neptune's migration dominated, resonances would play a stronger role. Observations continue to improve, and future surveys like the Vera C. Rubin Observatory's Legacy Survey of Space and Time may find many more distant objects, improving the statistics. As the catalogue grows, the belt might also help resolve the Planet 9 debate. If distant objects show clustering in their orbital orientations that is hard to explain by observation bias, it could hint at an unseen, massive body. If the clustering disappears with better data, the case weakens. Either way, the belt is part of the evidence. In the end, the Kuiper Belt is mind-blowing, not because it is dramatic in the moment, but because it is quietly rich. It is a slow archive of early conditions, a sculpted disk of small worlds, a source of comets, and a testbed for dynamics. It changes how we define planets. It extends the solar system's geography, and it reminds us that even close to home, there are regions we have barely seen. But to make those points feel real, it helps to slow down and imagine the belt as a place with locations, not just numbers. Not locations you could stand on in the ordinary sense, because most of these worlds are too small and too cold and too far, but locations in the sense of repeated environments. Near the inner edge, closer to Neptune, the sun is still present in a way that is hard to picture from Earth. It is not a warm disk in a blue sky. It is a bright, hard point in a black background. Shadows are sharp. The light has no soft atmosphere to scatter it. If an object rotates, its days are still long, but they are not endless. In this region, some bodies can still carry ices that react over seasonal cycles, but the energy is low. Every change takes time. Move outward into the middle of the classical belt, and the solar system feels more like a deep suburb. The planets are still there, but they are far away. Neptune becomes the dominant signpost, not because you can see it easily, but because its gravity organizes motion. This is one of the strangest ideas in planetary science. A planet can shape an empty-looking region without touching it. It shapes it through timing. If you plotted the orbits of resonant objects, you would see the same patterns repeating. The objects reach their closest points to the Sun at certain angles relative to Neptune. They reach their farthest points at other angles. The pattern is stable because the rhythm is stable. This is what it means to live inside a resonance. It is like being trapped in a slow dance step that repeats every few centuries. This is also where one of the 10 facts becomes more vivid. The belt is not a loose swarm. It is a set of lanes, and some lanes are protected by resonance. If you could watch the belt for 10,000 years, you would see these lanes as long-term highways. The objects are spaced far apart, but the structure is real. Now consider the cold classical objects again. Many of them are small, very red, and more likely to be binaries. This suggests a calm nursery. In the early solar system, when the gas disk was still present, small bodies could have formed in a gentle environment where relative speeds were low. In such an environment, pairs could form and survive. Contact binaries like Arakoth could form by slow merging. Wide binaries could remain intact. The survival of these systems is a kind of quiet proof that not every region of the outer solar system was torn apart. Then consider the hot population. Their inclinations are higher. Their orbits are more excited. This suggests a different history. It suggests that they were stirred, perhaps by encounters with Neptune during migration, perhaps by resonances sweeping through the disk. They may have formed in different locations, then mixed into the region we now call the classical belt. When you put these populations together, The belt looks like a layered record. Some objects are locals, some are immigrants. Now step farther outward, closer to the outer edge. The Kuiper Cliff is one of the most stubborn features to explain, because it looks like a sudden cutoff in an otherwise continuous disk. In everyday life, sharp edges often come from a sharp event. A cut, a tear, a burn. In planetary systems, sharp edges can come from resonances, migration, or external encounters. Each possibility carries a different implication. If the disk was cut short by a passing star early on, that suggests the sun's birth environment was crowded. If the edge is mainly a dynamical boundary created by Neptune and long-term stability limits, that suggests migration and resonance are enough to explain it. If the edge reflects where planetesimals could form efficiently, that suggests a change in the original density and chemistry of the disk. In all cases, the cliff is not just a fact about the belt. It is a clue about the sun's earliest neighborhood. Now, to build a more complete documentary picture, it helps to follow one imagined object as an example. Picture a small body, perhaps 100 kilometers across, made of a mix of rock and water ice, with traces of frozen methane. Its surface is dark and reddish, coated with organics that formed from radiation over billions of years. It rotates slowly, once every few hours, or perhaps once every day. It travels around the sun in a path that takes hundreds of Earth years. Most of its life is simple. It moves. It turns. The sky is black. The sun is a hard point. The distant stars are unblinking. Occasionally, it is struck by a smaller object. The impact digs a crater and exposes brighter ice beneath. Over time, radiation darkens that exposed patch again. Over millions of years, the object experiences a series of impacts that slowly reshape its surface. If this body is in a binary pair, the story becomes more complex. It may circle its partner every few days or every few weeks. Their mutual orbits can be wide enough that you could fit a line of Earths between them. Yet their bond persists because encounters are rare. In a calmer region, the pair can survive for the age of the solar system. But if the pair drifts into a region where Neptune's influence is stronger, the story changes. A close gravitational interaction could stretch the pair's orbit. It could unbind it. It could turn one partner into a lone traveler. This highlights another mind-blowing reality. The belt is a sorting machine. It sorts objects by stability. Some orbits last, some do not. Some bodies are slowly pushed into different classes. Over time, this sorting produces the populations we see. Now shift perspective to Earth. From Earth, the Kuiper Belt is not a visible band in the sky. It is something discovered through careful observation, through repeated imaging, through patient measurement. The fact that we can infer the structure of a distant population of small bodies from points of light on a detector is one of the quiet triumphs of modern astronomy. It shows what can be learned from motion and light, even when distance hides details. When surveys find a new Kuiper Belt object, the first measurement is its position, then its motion, then its orbit, then its brightness. Each piece adds information. Over time, the population map becomes clearer. The discoveries are not just about finding new worlds. They are about tightening the constraints on how the solar system evolved. This is why the belt is tied to the study of migration. Migration is not just a theory. It is supported by resonant populations. It is supported by the distribution of inclinations and eccentricities. It is supported by the existence of objects that appear to have been transported. The belt gives us a way to test these models against reality. A migration matters beyond our own system. Many exoplanet systems likely experience migration. Hot Jupiters probably moved inward. Resonances and instabilities likely reshaped many systems. By studying the Kuiper Belt, we study a nearby example of a system that still carries the scars of its early rearrangement. One of the most practical reasons the belt matters is that it changes how we talk about the outer solar system. It is easy to name the planets and stop. But the belt is a reminder that our system includes a vast population of smaller bodies that are still part of the architecture. They are still part of the story. In a sense, the belt is the solar system's memory. Now, if we return to the 10 facts and see them as a single picture, they form a clear set of themes. First, the belt is a real population, large in number, even if space between objects is enormous. Second, it preserves ancient material and chemistry that can help reconstruct the early disk. Third, it is shaped by Neptune through resonances and migration, leaving patterns that can be measured. Fourth, it contains dwarf planets and large bodies that expand our definition of what kinds of worlds exist. Fifth, it holds many binary systems that act as delicate probes of early calm and later disturbance. Sixth, it connects to the scattered disk and comet sources, linking the outer system to the inner sky. Seventh, it has a sharp outer edge that acts like a clue to a past event or a stability boundary. Eighth, it shows strong differences in surface color and composition, evidence of different histories. Ninth, it is a region where planet building stopped, leaving a fossil of incomplete formation. 10th, it continues to influence the present, and it helps us interpret other planetary systems. If you hold those themes together, the Kuiper Belt stops being a trivia fact and becomes a coherent place in the solar system. It becomes the broad boundary where the planets end, but the solar system continues. It becomes a region where gravity writes long patterns, where ice holds chemistry in place, and where time moves at a slower scale. And if you follow that thought to its quiet conclusion, you get something simple. The solar system is not just a set of planets. It is a layered structure of zones, each one shaped by different forces at different times. The Kuiper Belt is one of the most revealing of those zones, because it is both ancient and still present. It is distant, but not unreachable. It is dim, but not invisible. And it is still offering answers. There is one more angle that makes the belt feel even more real, and that is the way it blurs into other boundaries. The solar system has no fence. It has gradients. The belt grades into the scattered disk. The scattered disk grades into detached objects. Detached objects may grade into the inner Oort cloud. And beyond that, the gravitational influence of the galaxy begins to matter. This means that the far outskirts of the solar system are not only shaped by the sun and the planets, they are shaped by the wider environment. Over very long spans, the gravity of passing stars, the collective pull of the Milky Way, and the random chance of early encounters can all leave marks. When you look at the belt and the distant populations together, you are looking at the overlap between a planetary system and interstellar space. It is also worth noticing how the belt changes the way we think about distance and travel. A spacecraft leaving Earth can reach the moon in a few days. It can reach Mars in months. It can reach Jupiter in a few years. reaching Pluto took New Horizons almost 10 years. That is still within a human timeline. But it is a reminder that the belt lives at a scale where planning, patience, and reliability matter. A small correction burn done years in advance can decide whether a flyby happens at all. For the objects themselves, the same idea applies, but stretched far beyond human intuition. A slight change in orbit today can change a closest approach millions of years from now. A resonance can keep a body stable for billions of years. A rare close encounter can alter a path permanently. When you think in that timescale, the belt becomes a place where small influences add up. One way to see this is in the concept of dynamical lifetimes. Some orbits in the scattered disk are unstable on timescales of tens of millions of years, meaning that eventually the object will be moved inward, outward, or ejected. Other orbits are stable on timescales longer than the age of the solar system. The belt contains both kinds. This is another way the belt acts like an archive. Some shelves are permanent, some are temporary. And still, despite all this complexity, the belt can be summarized with a simple idea. The Kuiper Belt is where the solar system keeps its unused material. Not wasted material, but material that never became a planet. It is a ring of leftover building blocks, organized by gravity, preserved by cold, and slowly edited by time. That is why it continues to matter. Each new object found adds one more point to the map. Each new measurement of color, density, or binary motion adds one more constraint. And each new model of migration and early dynamics is tested against the belt's patterns. If you ever want a final mental image, imagine the sun as a small bright fire far away. Imagine Neptune as a distant clock hand turning slowly and setting rhythms through resonance. Imagine a broad, dim disk of icy bodies, each one moving in long silence. And imagine that in those slow paths, the early solar system is still written. Before we let the subject fade, it is worth briefly returning to a few specific names, not as a list, but as landmarks. Pluto is the most familiar landmark, and the reason is not only history. Pluto shows that a Kuiper Belt object can be complex. It has layered ices, weather, and a surface shaped by slow-motion processes. It shows that even far from the sun, a world can have active cycles. When New Horizons arrived, it revealed a landscape that did not fit the idea of a dead, frozen rock. It revealed a world that still changes. Haumea is another landmark because it shows what violence can do in the outer solar system. Its rapid spin and stretched shape suggest a major impact. Its family suggests fragments spread into related orbits. It is an example of how the belt can carry fingerprints of single events, preserved because everything out there moves so slowly. Eris is a landmark because it reminds us how incomplete our survey still is. It was found only in 2005, despite being one of the largest known bodies beyond Neptune. That means the outer solar system can still hide major objects. It is possible that other large bodies remain undiscovered in the dark, simply because they are too far, too faint, or too slow moving to stand out easily. And Arakoth is a landmark because it is small and simple, and because it looks like a gentle assembly rather than a smashed fragment. It is a direct hint that some parts of the early disk were calm enough for low-speed sticking and slow growth. These landmarks support the same core idea. The belt includes both calm histories and violent ones. It includes both ancient surfaces and reshaped ones. It includes both stable rhythms and scattered temporary paths. Even the way we detect these objects reflects those themes. A moving point of light can be an entire world. A slight repeated dip in a star can reveal a ring. A binary orbit can reveal mass. A faint infrared glow can reveal size. The methods are quiet, and they match the subject. If there is a final lesson in all of this, it is that the outer solar system rewards patience. The Kuiper Belt is not a place of fast events. It is a place where the most important actions unfold on timescales too large to feel directly. The story is there anyway, in the structure, in the resonance patterns, and in the preserved material. One last thought makes the whole picture feel even larger. When you stand on Earth and look up, the solar system is invisible as a structure. You see the moon. You might see a bright planet. With a telescope, you can see more. But the true architecture, the belts and populations and resonances, is something you have to build in your mind. The Kuiper Belt is one of the strongest reminders that the solar system is a system, not a lineup. It is not just 8 planets and a few odd leftovers. It is a set of zones shaped by gravity and history, with the Kuiper Belt acting like a broad outer memory. If you could compress time and watch the solar system from above, you would see the planets as bright beads on fast paths, and farther out, you would see a much slower haze of motion, a wide ring of small worlds turning in long silence. In that haze, the early disk still echoes. Neptune's migration still shows itself, and the unfinished work of planet building still has a place to remain. And for all its distance, the belt is not separate from us. The water and carbon in our own world came from the same early disk. The comets that occasionally cross our sky come from these cold outskirts. In a quiet way, the Kuiper Belt is part of the same story that led to Earth. In the dark beyond Neptune, the archive stays open and the evidence keeps drifting, waiting to be read. And slowly, survey by survey, year by year, the map improves, and the outer solar system becomes less like a rumor and more like a known coastline. This was a quiet archive story, where the story ends, sleep begins,